Hi everybody, welcome back. This is going to be a fun project, and I'm doing this after I've just filmed the whole video. And I'm doing this to just kind of give you a heads up what we did. So what I've done is I've taken one of the preamps of these CA2000s and I replaced all of the audio path capacitors, at least the ones I could practically do, with film capacitors. So any place that there was a electrolytic of any type, polarized or non-polar, whatever, I actually replaced it with a film cap. I also recapped the rest of the preamp, checked all the transistors, did all the same maintenance and so forth that I did to the other preamp. So they're identical other than the difference between the film capacitors and the electrolytics being in the audio path. Then I went and connected this to the difference amplifier, and we checked some different frequencies, and we checked using a pink noise generator fed equally into both preamps against one another, and we looked at the difference between the two preamps. The other thing I did was, after looking at it in the time domain to see, the nulled signal, I then went into the frequency domain and looked at it on a spectrum analyzer. Now, there was one caveat to that spectrum analyzer, and that is there was, at low frequency between 20 and around 100 hertz, there was a little bit of noise, and guess what's in that, what lives in that, and that is 60 cycle hum, or 50 cycle hum in some countries, but here 60 cycle. So 60 and 120 are the two frequencies that you can see mains noise. And there was a little bit on there, and I attribute some of the differences we're seeing here to that. And we kind of, at the very end of the video, I kind of come to that conclusion a little bit. I have shot a ton of clips. Some of them I'm going to scrap because they were just me thinking out loud and so forth. And this would be a very long 2-hour video if I put them all in there. So what I'm going to do is try to show you the important highlights of what I did throughout the process. And at the end of the day, sorry, haven't had my second cup of coffee yet this morning. At the end of the day, my conclusion, spoiler alert, turn this part off if you don't want to know. My conclusion is there's very little to no difference between good quality electrolytic capacitors and film capacitors in the audio path. That being said, remember that we did videos on, for instance, that Marantz 2240 that's still sitting on my bench is my bench amp, where a film capacitor actually allowed, parasitic oscillation to take place in one of the capacitors or in one of the transistors, whereas fitting in the original electrolytic cap, that noise went away. So yes, there are instances like that I think you could have, and you have to watch out for that pitfall. But as far as audio quality goes, I know that I went through that Cyril Bateman, all of his articles and so forth, and I mentioned him in the video too. Definitely he proved that there is a difference in distortion in capacitors versus, the film versus electrolytic. But it was, when I looked at the numbers he was showing, they were so astronomically tiny that, to me, why are we even worrying about this? That was kind of my opinion on it. So anyway, enjoy the video. If this is the kind of thing you're interested in, you might like this video. If you're a less technical person, this one's going to be just super boring. I have some other things that coming up, some restorations and things that we're going to do next. So fear not. But anyway, enjoy the video. Okay, you can see I'm wearing a different shirt. It's a different time. I've finished editing the video, and I'm going to stuff this one last little comment in here before we start. And that is, if you go back a couple videos, I did a pretty exhaustive test on capacitors and on how electrolytic capacitors do have a different frequency roll-off characteristic than a film capacitor. I still believe that because we tested it and we proved it. The tests that we're going to do in this video now are going to show that even though that's the case, it doesn't seem to, at least in this circuit, in this preamp, it doesn't seem to make a difference. There's reasons for that. That might be something that I'll do in a short video at another time. For instance, in a polarized electrolytic capacitor, believe it or not, you can put alternating current into a polarized capacitor. But you have to remember, the capacitor is going to have a much smaller capacitance in its reverse direction, reverse polarity direction, than it will in its forward polarity direction. Okay, so that's the first thing. Second of all, the amount of voltage that a capacitor can handle, a polarized cap can handle in reverse, is way, way lower. So one of the ways that these manufacturers got around that and still used a polarized cap in an AC situation is, number one, they made sure the capacitance, the forward capacitance, was much higher than it needed to be. So that's why it's not uncommon to see a capacitor that might be 10 or 20 microfarads, when you really only need, if you did the math, you probably could get away with just a 1 microfarad capacitor, because when that capacitor is going in reverse polarity, it's only that 10 microfarad capacitor may only be a 1 microfarad capacitor, which is still well within the design limits of the circuit. See how they do it? So that's number one. And number two, when it comes to those frequency roll-offs and so forth, the design of the circuit actually takes care of those anomalies. So even though we've proven that there's differences in these types of capacitors, the design of the circuit makes it null and void. That's my opinion. Okay, that's a spoiler alert, but keep that in mind as we go through these tests, because this is a pretty interesting video, at least to me it was. To those of you who aren't really into the technical end of things, this is worse than watching paint peel. But for me, it was exciting, and I learned a lot, and it's actually changed my perspective on this. So let me insert this at the beginning of the video, and then we'll get started. Hi everybody, welcome back. So this is the Sansui CA2000 from the very first video in this series. This is the one that we only replaced those couple of resistors and got it working, and we tested it, and if you recall, it really performed well just as it was. And then we went and we had a second CA2000 that was in a little better condition, and we did a full restoration on that. We replaced all the capacitors, all the bad resistors, cleaned it up really well, powder coated the covers on it, and it's ready to go. Now what I'm doing with this one is something a little different. I am going to do a recap on this. I'm going to replace the rest of the bad resistors. I already found a couple of them on the phono stage board, which were replaced. And what I'm doing right now is, during this recap, any power line filtration type capacitor, I'm replacing with the same caps that I used on the other CA2000. However, anything in the audio path that is reasonably able to be replaced is being replaced with film caps exclusively. In other words, any of the bipolar electrolytics and any of the polarized electrolytics that have anything to do with the audio path, not just like power supply filtering, are being replaced with film capacitors. So if you look on, for instance, the volume control board, you can see all these white capacitors. You can kind of see them down here and up in here and all around. Those were all electrolytics. If you look down on the tone control boards and on all the different things down here, you can see all these red capacitors. Those were originally electrolytics. And any of these electrolytics do not directly fit in the audio path. They're just used to kind of clean up noise on the DC supplies coming into the board. So they've been replaced with the same caps that are in the other CA2000 that I recapped. So I'm going to go through this whole thing, and when we're done, all the audio path capacitors will be film. And then we're going to compare the two. Okay, this is going to be total experimentation on my part because I have no idea if this is even a worthwhile test or what it's going to show. But as you can see, I have the two CA2000s stacked on top of one another on the bench here. And I marked this one as lytic, for electrolytic. And this one is the film capacitor one that we just did in this video. So this one has film capacitors anywhere in the audio path that I could practically put them, I should say. And there were two areas where I could not put film, and that was only in the headphone amplifier, and that was because they were very high values. One of them was 10 microfarads, the other was 220 microfarads, and they were directly in the audio path. But a 220 microfarad film capacitor would be absolutely huge, but you can see right there is the 220 and right there's the 10. They are directly in the audio path, but we're not using the headphone amp. We are actually just using the preamp itself. So the output of the preamp does not go through this. Now, this is only if you want to listen to headphones. So if you look at this little schematic that I printed out, I put some notes in it and so forth, but wherever you see these circled caps, all of those are either bipolar or polarized electrolytics in there, and they've all been replaced with film caps. So this is definitely going to be a test of the difference between a film capacitor and an electrolytic capacitor in the audio path. And we're using two identical preamps, and they both have been restored. So they've been recapped, as far as the power supplies and everything are concerned. I've used the same components in both of them. So these are as close as I could get to one another without getting ridiculous. Let's just put it that way. So the only differences should be the film caps versus the electrolytics. Now I could just use sine waves and so forth, or we could try like a two-tone SMPTE waveform, where you use the 18 and 19 kilohertz against one another and things like that, and look for harmonics. And maybe I will do that, I don't know, but I'm really more curious about, and this is why I built this in an earlier video, about pink noise. I'm going to feed a pink noise signal, equal signal, into each preamp. Of course, these are stereo preamps, but we're only going to test one channel of each one. That's all we need to know, because we know they match one another right to left. So I have the right channel of this one and the right channel of this one connected to this pink noise generator. And the outputs, the right channel outputs of these, are each going to one channel of the scope. So I'm using two channels of my oscilloscope here. And the first thing I want to do before we try any kind of tests is I want to try to balance the two signals as closely as I can. So what I'm going to do is I'm going to turn up the first preamp and then the second preamp. So the first one is going to be the yellow trace. And you can see as I turn it up, that's that pink noise. And again, we're not looking at the spectrum of the pink noise. We're looking in the time domain, not the frequency domain. So when you're looking at a random pink noise generator, you're going to just see static. That's what it's going to look like. So I'm going to turn this up, and I'm at 200 millivolts per division. And I'm going to get a fairly decent looking signal. I'm about halfway turned up. And I want to try to get this, around half volume level, something like that. So there's a decent output. Now I'm going to take the second preamp, which is the blue trace, and I'm going to try to turn it up until we can no longer see the blue trace. I want it to kind of disappear into the yellow trace. So I should see no blue at all. See, I'm still seeing little flashes of blue. Now it's starting to disappear. You can see you can't see any blue at all. And if I go to channel 2, again, I should see no yellow. See, the yellow is kind of just popping up above there a wee little bit. So I'll go a little bit more. And there, the yellow is all gone for the most part. Can you see that? So what that means is that I have these two preamps set to have equal output with equal input. So they have the same amount of gain right now in them. And really, I would argue if you could adjust the input a little better, you could turn the volume control all the way to maximum and take out the variable of the potentiometers and so forth. But I don't like that idea because when you crank these the whole way, that's going to allow it to introduce a little more noise, which I really don't want that right now. So I think I'm just going to do it this way. Again, this is all subjective and this is all me experimenting. And I'm doing this live on camera. You're going to actually see as I see the results of this. I'm trying to find the best way to kind of prove whether there is or isn't a difference between using electrolytic and using film capacitors in these two preamps. And the only way you could do it is in a controlled environment using two of the same device. So these are both CA2000s. They've been restored. I'm trying to make this as fair of a race as possible. Now the next thing I want to do is I want to be able to look at the difference between the two channels. One method would be to use the math button. And we can use the math button and we could subtract the one channel from the other. And technically you should be able to have a straight line for the red line, which would be the math, and it would show you the difference. The problem with doing that is you have to really, to get it perfect, you have to be able to null out any differences between the two channels first of all. And to get it to null out properly, you can't get fine enough adjustment. You'll see, just turning up the volume on the two preamps, what I found is too touchy. So you really need a better way to do it if you can. Okay, this is one way, and this will get you pretty close. But a better way would be to use our little project we made a few videos ago, and that is this difference amplifier. And these are 10-turn pots on here, so we can really fine-tune the null point with this. So I'm going to set this up, and then the other thing that's going to allow us to do is if there is a very, very tiny difference between the two channels, this actually has an amplification of up to 11 times. So I can actually amplify that difference to make it more visible, if that makes sense. So there's a few advantages to using this. Is this craziness and overkill? Maybe, but hey, this is my channel. It's fun. This is my hobby. So let's hook this up and see what kind of results we can get. Okay, hopefully I'm all in frame. So I have the two outputs of these two preamps. I just took them out of the scope, channel 1 and channel 2, and I put them in channel 1 and channel 2 here. And then I connected the output of our difference amplifier into channel 1. Now, you can already see that on the scope, as I mess with my camera again, I should probably do this off screen. You can see where it's already pretty well nulled out. There's really nothing there. Now I'm looking at 200 millivolts per division. And let's take the scale down even further. Let's go to 50 millivolts per division. And you can see they're still pretty much nulled out totally. So now what I'm going to do, I'm going to back up so you can see what I'm doing. I'm going to increase the gain on our output here to just amplify that difference between the two channels. And you can see right there, now It's about 11 times more than the actual output. So all that does is that changes, as I bang the camera, that changes this scale. So now instead of being 50 millivolts per division, you're looking at a little bit over 4 millivolts per division, if that makes sense. So really this difference, the difference itself, it's saying the RMS of this signal is about 55 millivolts on average, and you see it bouncing around down there. So really it's about 4 millivolts. So there is a very, very, very tiny difference between the electrolytic preamplifier and the film capacitor preamplifier. That's what that's telling us. Now, if I adjust one of these channels, I should be able to null it out even more, but I have a feeling it's already there because we got it pretty close. But let's see what we can do to null it out even more. Look at that. There it is. Check that out. By nulling this out like this, and I barely touched this 10-turn pot. This is a 10-turn potentiometer. I just barely turned it about a quarter of a turn. I was able to bring the null point even closer than we could physically do by using the volume knobs. And now you can see the true difference between the two channels. Now we can't tell what frequencies those are. We can't tell if that is distortion because we're looking in the time domain right now. But now we can switch to the frequency domain. So let's go Option, Spectrum Analyzer. And you can see right now, I'm not seeing much of anything at the moment. So let me adjust the sensitivity of this and see if I can get something to show up. Okay, I've now adjusted the spectrum analyzer as best I could. And you're just seeing just the tiniest little bit of difference. I had to set this scope to the highest sensitivity to even be able to read anything. And the white trace that you're seeing kind of superimposed over the orange or the red trace is the average. So that's basically averaging out the random noise. And you can see that you have a little bit of difference between the two preamps at the extreme bottom end of the bass frequencies. So down around, and remember this is pink noise, so the bass frequencies are higher, and they slope down at 3 dB per octave. And we talked about that when we did the pink noise generator. Okay, I just noticed my my record shut off again. So let me do this all over again. That's the only thing about this ZV-1. It'll come out of record without telling you. I mean, it might beep, but my hearing is not so good. I may not hear it, but it won't stay on for a long time for a video clip. I don't know why it does that. It always has. I just have to monitor it. So what I've done right now is I turned off the real-time spectrum and I'm looking at the averaging. So I'm taking 64 sweeps and averaging it and showing it as this white trace. And you can see, okay, I'm making sure the record is still on. You can see at the bass frequency, so for the first octave from 20 hertz to 40 hertz, you can see there is a phase shift on one of the preamps that is not happening on the other preamp. So there's a phase difference between preamp 1 and preamp 2, the electrolytic preamp and the film capacitor preamp at low frequencies. You can also see 4 spurs here, and they're not at harmonics, I don't think. So there's 1, 2, 3, 4 spurs. And if you're perfectly nulled out, you can see those spurs. If I adjust the null point, come out of the null point, I can get them to be buried in the noise floor a little bit. This one here doesn't totally go away, but pretty close. And if I bring it back into null, you can see those little peaks pop up. Let's see if I can get it to... Right there's the null point. See where it like starts to go back up again? Right about there. And you can see those right there. So to me, that tells me that there is a difference in phase response between the two preamps. So now that we have this evidence, how do we prove which one is which one is the culprit? Where is this coming from? You know, that's what I want to know now. Okay, I tried adjusting the resolution bandwidth a little more. I went from a resolution bandwidth of 10 hertz down to the minimum that this thing can do, which is 4 hertz, which really slows it down. But you can see it really didn't change anything. You can still see those spurs. They're a little more prominent now, but there's definitely a difference between those. Now, if I turn one of the preamps off, so let's turn off the one with the film capacitors. And you can see there's no spurs in that one. And you can see that pretty much looks like a pink noise signal. And if I turn the other one off and turn the other one on, so now we're looking at the one with the film capacitors. We were looking at the electrolytic one before, now the film. It looks pretty close. You have a couple little dips in there. You see there's one here. So tiny, it's hard to see. One here, almost in the same spot where you saw those little pips when you were comparing both. So you can see the one with the film capacitors does have a tiny little bit of distortion or phase shift or something. So I think it's the one with the film caps that's the culprit. Turn them both on again. And see what happens. And there you go. When they're both on, you can just see those little pips again. So there you go. There is a difference between film and electrolytic capacitors. It is very tiny. Okay, turning off the spectrum analyzer. Turning off the pink noise generator. So we are now looking at silence. You can still see there is a little bit of noise here at the low end. And guess what is in that area right there? Yeah, you guessed it. Mains hum. You know, your 60 cycle or 50 cycle hum. So let's turn off the film capacitor one first. And let's see what happens. Look at that. Holy moly. Okay. So now we're looking at the one with the electrolytic capacitors. Let me turn both of them off. You got to wait for it to stabilize. I'll turn the camera off and back on after it goes through a few cycles here. So here's your noise floor with no amplifier turned on. Now let me turn the one with the film capacitors on and see if it changes. Oh yeah, there it goes. See it climbing? That's your 60 and your rectified, 120 hertz. That's your hum in the preamps. And they both have very similar. Looks like the one with the film caps is a little bit more, because see how it carries out a little more? But they're both similar. And I don't think that has anything to do with the film versus electrolytic caps. That just has to do with the design of the preamp. Remember, we are looking at teeny little signals that, we're amplifying 11 times out of this, this thing. So we're picking the fly crap out of the pepper, you know what I mean? And this is nothing to be concerned about. This is not going to, even with a, connecting this up to a 200 watt amp, I don't really think you would hear much hum in the background unless you cranked everything up the whole way. Remember, I have the volume controls turned up to about 1 o'clock almost. I'll show you that. if you look down here, that's about where they both are turned up. You can see that also shows that the volume pots are pretty matched between the two preamps. So there you go. You can get a lot of information off of this. What happens if I disconnect the connectors altogether? Let's see what happens. Do we get rid of the noise? See it drop? It's going to take a few minutes, so take a few seconds, so let me come back. Okay, so there is, with nothing connected, that's your absolute kind of noise floor coming from my difference amplifier. So some of that noise is coming from my difference amplifier, not from the preamp. So let's go and check here. You guys bored to death yet? So I have these both turned on now. Let's go to, I have nothing connected to the oscilloscope now. And let's see if how much it nulls out. You can still see some low frequency component there. I think that's an anomaly of the scope. That's our test equipment. How interesting. So even with nothing connected, it's pretty flat now, isn't it? This is a pretty quiet little difference amplifier, but so you can see even with nothing connected to the scope, there's a wee little bit of mains noise in there. And part of that has to do with the scope itself, but it's pretty, insignificant. That's about as quiet as it gets. If I connect up the difference amplifier, there's your noise floor of it, and you can see it does have some noise, and that's because I have it set to a gain of 11. If I turn that down to unity gain, it'll probably drop down. You can see it's already starting to drop. It takes a while with this averaging. You just have to be patient and let it do its thing. But you can see this thing's very, very quiet. It's not bad. And there is a little bit of noise here. So again, maybe there isn't as big of a difference between the two preamps as I had originally thought. Okay, I am seeing some noise in here. See those little pips? And that's between the two channels. So let's connect the preamps one at a time. So here is, take this out, here is the one with the electrolytic caps. It's turned on. I haven't changed anything, but I just have the signal turned off. There's no, right now there is no pink noise generator connected. And you can see there's no noise at all out of that preamp, nothing. And by the way, that puts a load across the input of the spectrum analyzer, which quiets it down even more. So you can see everything dropping. So there is absolutely no background noise in the preamp. Let's hook the other one up now. So I'll disconnect this one and I'll connect the one with the film capacitors. And I wouldn't expect any noise to be any different. So you see a couple little pips showing up here. Again, I don't believe that to have anything to do with the film capacitors. And you can see we are getting noise. And that is, well, each one of these represents 2 kilohertz, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So right around 5 kilohertz, right? Or no, 3 kilohertz, 2.5 kilohertz, 2.5. There's one right there. That's a big one. Noise that did not exist on the other one. So I think there's a little bit of noise in that preamp down there is what's telling me. Just the tiniest little amount. So what's my overall opinion now after we did this experiment? My opinion is that at least in this circuit, in this preamp, it makes absolutely no difference if you put film capacitors or good quality electrolytics. It will not make a difference. One can make the argument that the electrolytics possibly won't last as long as the film caps. Although I've had film caps that deteriorated and broke down over time too. So is in the same time that it takes for the chemistry of an electrolytic to break down. So again, that's really not a big deal to me. What else can I say? This is a good preamp. It shows us that. This one has a little bit of noise in it. This one is quieter. But again, I don't think that's capacitor based. I would think if anyone was going to be noisier from the capacitors, it would be the one with the electrolytics. So to me, if you have a capacitor that meets the specifications that they're supposed to be, I don't think it makes a hill of beans a difference which caps you use on that. Just so they're high quality, just so they are, audio grade where they will actually, work within the audio frequency range. It won't matter if they're film or electrolytic, in my opinion, from this experiment anyway, okay? There's always going to be people that can say they can hear the difference. And I myself have thought I've heard a difference, but I've never done a one against the other test before like I did on this. So I've really kind of looked at this from whatever angle I could, other than listening to it. And I can't do that on video because you're not going to hear through the microphone and the compression of YouTube and everything. You're not going to hear reality. But I mean, I could listen to it here and kind of give you an opinion, but I would tell you with my hearing, I probably wouldn't notice a difference. I think these are both equally good performers. And again, the circuitry is designed to correct for things. I mean, that's what negative feedback and filters and all that. That's what this is all about. Current mirrors and, current sources, all these things that they do in here, they're designed to keep that frequency response flat, even when there's little differences in the components. That's the whole thing. A well-designed circuit will not be affected by the components as much because they will dynamically adjust around the components, the little changes in the components. There are no two transistors that are alike. If I take 100, KSC 922s and I characterize all 200 of them or whatever, they're all going to have tiny slight differences in gain, in VBE, in noise, all kinds of things. And if you have a circuit that's going to be highly dependent upon those characteristics, you're going to have an unstable circuit. So these folks spent years and years refining the circuitry to be able to compensate for those differences and null them out. And this is a good example of it. Now, if either of those components were physically bad, like the capacitors, that they actually weren't working properly, they had developed really high ESR or something like that, or a short, bad leakage, certainly that would change some things, because that's kind of an extreme case. But little tiny minute differences, I really don't think it's going to affect it. I mean, that's kind of where I am with it. That's maybe why I like this stuff so much. It's just so well designed. And I do like the little imperfections in it too. That's part of the character, that why people like classic audio gear over some of the more modern integrated gear where everything's on a chip now. So it's a matter of opinion. But this was an interesting and fun project to do. I like doing this. It was cool. These are ready to go off the bench. And hey, what can I say? So I wish you all peace, joy, happiness, and good health in your lives. I hope you had fun watching this. I definitely had fun making this. Take care, everybody. Bye-bye.